So the next mathematical process we need to make sure that we're able to do with vectors is vector subtraction. And again, vector subtraction works pretty much the same way vector addition does. So being good at vector addition means we're probably very well set up to be able to do vector subtraction. And again, it really just fundamentally comes down to, can you break vectors up into their components? So graphically, let's talk about what vector subtraction means. And there's a couple ways that you can think about it. They're going to give you the same answer. Well, one way to think about it, what we'll call sort of option one here, is that it literally is as simple as it's the vector that goes from the tip of B to the tip of A. So if you draw your two vectors from the same origin, the vector subtraction problem is literally, or one way graphically to draw the vector subtraction problem is just to draw from the tip of B to the tip of A. So whatever you're subtracting, that's where you start. Whatever you're subtracting from, that's where you finish. So there's A minus B. Okay. The second option we've got is, well, I can think of A minus B as really a vector addition problem where what I'm adding is negative B. And one of the things we'll talk about is, well, negative B is really just negative 1 times B. Well, negative B just points in the opposite direction. So if B pointed up and to the left, negative B points down and to the right. It's both of them make a 20-degree angle with the y-axis. So basically all I've done is I've just flipped vector B over to get vector negative B. And then this is just a vector addition problem, so I want to slide them so that they're tail to tip and now connect from first tail to last tip. So you'll notice that when I was drawing it initially, it was drawn up here, right? A minus B was drawn up here, but it had the same magnitude and the same direction. So that means it's the same vector, right? We don't care, right? Vectors don't depend on where they start from. They only care about magnitude and direction. So either way gets me the same vector A minus B. So graphically, that's what we're doing. In terms of how you're going to work vector problems, vector subtraction problems, well, again, basically, you're going to do exactly the same thing we did for vector addition. We're going to take our two vectors and we're going to break them up into components. The only difference is, instead of saying this plus this equals that, we're going to say the x component of A minus the x component of B equals the x component of C. So again, we've got a two-dimensional vectors, so we've really got two equations folded in here. One for x components, one for y components, and that's all we're going to do is we're going to say, oh, the x component of vector C is nothing more than ax minus bx. And so one thing to emphasize, in our vector addition problem, order didn't matter. In our vector subtraction problem, it clearly does. So here I would have 12 cosine 25 minus negative 8 sine 20. So again, this really means that I'm this minus a negative, so this is really adding together, so I end up with 13.6 newtons as my x component. So here's equation 1 for x. Then equation 2 for y says y component of A minus y component of B equals y component of C. Again, plugging in those values gives me negative 2.45 newtons. So same process, break up into components. All we're doing is now subtracting where we need to rather than adding. I still get my components for vector C, and so again, if I want the magnitude of vector C, I would just Pythagorize. So 13.6 squared plus negative 2.45 squared, take the square root. If I want the direction of vector C, right, the direction of this subtraction, then again, I'm going to take the inverse tangent of, and if I put the y component over the x component, then that will tell me this little angle relative to the x-axis. So vector subtraction, very much like vector addition, you're just subtracting rather than adding.